In this section, we're going to be studying what's called extrema. And as the first sentence states here, the minimum and maximum of a function on an interval are the extreme values or extrema. Extrema would just be the plural for extremum of the function on the interval. Now, when you're talking about extrema, that can consist of relative maximums and minimums, but also absolute maximum and minimums. And these are all things that you have discussed in the past in other courses, but we're going to be using derivatives to help us determine these things. Now, one thing I want you to keep in mind is that for right now, in this section, we're discussing this based on having a closed interval, and later we'll still be discussing these things, but we won't be restricted to a closed interval. All right, so your extreme value theorem states if f is continuous on a closed interval, so from a to b, this is representing your closed interval, then your function has both an absolute minimum and an absolute maximum on that interval. Now, when you've studied absolute maxes and mins before, you have learned that you don't always have to have that with a function, but when it's in reference to a closed interval, then you will always have both of those. All right, looking at the graph here at the top for just a minute, the first one would represent a graph that is on a closed interval because it does not go to infinity or negative infinity at the left end or the right end, either one. You have the closed in dots at each end here that represent that the graph stops there, and of course the fact that it's closed in indicates that it's on a closed interval. Okay, so if this were our graph, the point that I have here at the top would be considered your absolute max, because it is the highest point that you have on this entire graph. But now the point that you have here, this would be considered your absolute min, because it's going to be the lowest point that you have on that whole graph. So sometimes you'll see that the max occurs or the min occur at an end point, but it doesn't have to. It can occur somewhere in between the ends. Now, the second graph that I have here is not on a closed interval. It is closed at the right end, but as you can tell, the left end keeps going down forever. So actually, this extreme value theorem is not describing this situation at all, because this is not a closed interval. But I just wanted to point out to you the fact, like, this would be your absolute max, just like it was a few minutes ago. But this graph would not have an absolute min because it turns and goes down forever. So the only time that you're guaranteed an absolute max and an absolute min, as it says, is going to be on a closed interval. Okay, you are asked to find the value of the derivative at each of the relative extrema. All right, so they are listing this being a point, so at the point 3, 2, that is going to be an extrema, which I gave you the list a while ago. What consisted of extrema were your relative maxes and mins and your absolute maxes and mins. But let's see what happens to our derivative at this particular point. So first thing we've got to do is actually find our derivative. Now, what I would suggest you might want to do right here, you don't have to distribute the 9. I'm going to go ahead and distribute. So when I use my numerator, I'm going to refer to it as 9x squared minus 27. Okay, you are going to need to use your quotient rule. So we'll have low d high minus high d low. And that would be all over low, low. Okay, so now doing some simplifying here. Of course, you can multiply x cubed times 18x. Okay, now you need to distribute the 3x squared. Go ahead and treat that as a -3, and that way you'll take care of distributing the minus sign at the same time. So that means that you would have a -27x to the 4th, and that would end up being plus 81x squared. Of course, here you have a power to a power, so this would be x to the 6th. Okay, you can combine your 18 minus your 27, and that's going to give you -9x to the 4th plus 81x squared. Okay, I have a common factor in my numerator of -9x squared. So that's going to leave me with a positive x squared minus 9, and that would be divided by x to the 6th. Okay, you can do some reducing here. The x squared that you have on the top will cancel with 2 that you have on the bottom. So now you're going to have -9 times the x squared minus 9 divided by x to the 4th. Okay, now that's our derivative, but now you're asked to find the value of the derivative at the stated extrema. So the stated extrema was the 0.32. So we're going to evaluate the derivative at 3. Now you don't need the whole ordered pair, you need just the x coordinate because x is the only value that you have in your derivative here. So just substitute this in. Of course, you can use your calculator to help you find your value. Of course, your 3 squared is 9, 9 minus 9 is 0, 0 times -9, of course, is 0 over 81, which is going to give us 0. Now, remember, derivative is the slope of the tangent line at that point. So, on this graph, at the point 32, we have a slope of 0. So, what type of line always has a slope of 0 would have to be a horizontal line. Now, I've gone ahead and graphed this in the calculator. This is the function that we're working with here. And if you locate the point 32, that would be here. Which that is actually an absolute max for this particular function. That's going to actually be the high point. It comes up with a little bit of a hill, and then it gradually starts coming back down right here. So this being a max, that's the high point, so that would mean, you know, I just lightly dotted it in there, your tangent line would have to be horizontal in that particular case, okay? Now, one thing that I want you to think about is if you're talking about the high spots of your function or the low spots of your function, which is where your extrema would have to be, that's where your maxes and mins would have to occur, you're going to have to be seeing, like in this case, a horizontal tangent line. So the fact that you're getting 0 for this value shouldn't surprise you, because again, if you're at the top of a hill, the tangent line should have to be 0 if you're at the bottom of a valley. Okay, next example. Okay, so we're asked to do the same thing on this one. What I have in the box here is something that we actually dealt with back earlier. But I just rewrote it just to refresh your memory, because that's what we're going to have to use. Okay, so you're needing to take the derivative, because we want to know what is the value of the derivative at the point 0, 0. Now, let's just kind of discuss the situation that we have here. The absolute value, of course, is a function that you should be familiar with. All absolute value functions are those V-shaped graphs. And of course, this one has no transformations to it. So actually the vertex that you have at 0, 0, or the vertex is located at 0, 0. So I want to go ahead and look at it. Okay, so here's 0, 0. So that's going to be the place that we're going to get the value of the derivative. Now, if you remember back with derivatives, there were certain situations in which your derivative did not exist. And one of those situations was that your derivative did not exist at a sharp point. So the fact that the point that we're given here, 0, 0, happens to be the sharp turn or the sharp point of this particular function, when I go to take my derivative and evaluate it, I should expect to get something that does not exist. Because based on what we know about derivatives, this should not exist. Now, you've not learned a rule, like product rule, quotient rule, you've had your trig functions. You've not learned anything concerning your absolute value. So that's where in the past we had used our alternate form to do this or to help us figure this out. So we're going to take the limit as x approaches 0, and I'm going to go from the left first of all. Okay, so I need my function f of x minus f of c. Of course, what we're looking at here is the point 0, 0, divided by x minus c. Okay, now I didn't put in my function just yet because that's actually where this comes in. When you're dealing with values in which x is bigger than 0, then you're looking at the portion of the function that's described by just x. If you're dealing with values that are less than 0, then you're dealing with the portion of the graph that's represented by just negative x. If you're coming in from the left side, then you're dealing with the values that are less than 0. So my function in this case, I would need to use the negative x. Now, if you are to evaluate your function at 0, absolute value of 0 is just 0. Of course, on the bottom, you've got x minus 0. So that's just negative x over x, which gives us negative 1. Okay, now if I do the limit as x approaches 0 from the right. Now, this time coming in from the right, I would have to use this portion of the definition for absolute value. And again, the function evaluated at 0 would be 0. So I get x over x, which is positive 1. But the fact that the limit from the left and the limit from the right are not equal to each other, that tells me that my derivative does not exist. Okay. So therefore, as far as the value of the derivative at 0, 0, it does not exist. But going back to what we had talked about a while ago, that's what we should have expected to see something like that happen, because that is a situation in which you have already learned your derivative doesn't exist at a sharp point. Okay, let's see one more example with this definition. All right, so let's start with our derivative. The derivative of sine is going to be cosine. And now I need to evaluate this at pi over 2. Okay, If you remember your cosine graph, of course, pi over 2 is the same thing as 90 degrees, but that is where you would have a value of 0. Okay, let me just sketch this off instead of taking time to put it in my calculator, but remember your cosine graph, of course, this being pi over 2, this being pi. Okay, so see, that's where you can, just going back, helping you with this value. Of course, this is your cosine graph. This is not this one. So whether you're looking at your graph or if you're remembering, you know, like from your values, cosine at pi over 2 is equal to 0. Now, tying this back to this though, again, what we're asked is the value of the derivative. Okay, so this comes out to be 0, then that would tell me that my tangent line has a slope of 0, which would indicate that it should be positive. Now, that would be the slope of the tangent line of this original function. I just drew this off to help you remember that cosine of pi over 2 is equal to 0. But now recall your sine graph. If you remember your sine graph, that should be positive 1, negative 1 down here. So your sine graph goes up at pi. So see, you would have a horizontal tangent line here at pi over 2.